Welcome back to Bit of a Tangent. And it's good to be back. So today we're bringing you the first in a series of what should be 3 episodes where Gianluca and I dive fairly deep into predictive processing theories of how brains like ours can come to understand something about the world in which we live. Many of you will know that we have teased this episode for quite some time, and I'm thrilled to finally put it out there. Predictive processing, or predictive coding as it's sometimes called, is a compelling theory in neuroscience that explains many of the otherwise puzzling things that seem to be true about our brains. Most importantly, the reason it's so compelling to talk about is that there are many facts you can learn in neuroscience. You can learn which receptors are located on neuron cell membranes. You can learn which neurotransmitters cause those receptors to open and how that causes the neuron to fire. You can learn which neurons are especially sensitive to faces through things like fMRI. You can learn which parts of the brain are connected to which other parts. And you can learn about how neurons in different parts of the brain look different and do different things. But nowhere in this list of facts you might acquire in a popular book about the brain, or even in a textbook of neuroscience, will you receive a clear mechanistic explanation of how any of those facts relate to actual computations your brain is doing, and how your experience of the world is related to what it's doing. Of course, on some level, scientists are still unsure, and the final answer clearly hasn't been found. But there are things to be known about what is going on in the brain, and unlike a list of disconnected facts, predictive processing has interesting, often profound things to say about how brains work in general. And that's what we'll be getting into over the next 3 episodes. In this introduction, we motivate the predictive processing view of the world, discuss the difference between top-down and bottom-up perception, the primacy of Bayesian brain hypotheses, the logic of only caring about prediction error, and the phenomenology of visual illusions, as well as a lot more along the way. As always, I hope you enjoy, and here's the next episode of Bit of a Tangent.
Predictive processing is the 900-pound gorilla of an episode that we have been teasing so long as to, I don't know, just reduce our audience to maybe 0. No one's listening anymore.
When we say hype, we don't mean that lots of people have been saying, "Oh, please do that episode." We just mean the two of us are saying,
exactly.
We should really sit down.
In fact,
and do this.
I think in the last 3 episodes we've mentioned predictive processing or predictive coding more than Eliezer Yudkowsky on average. So that's
which is almost.
I'm pretty sure there's a theorem in information theory that prevents that from being possible, but somehow we've managed. So that's us. Here we are, folks. It's the one you've all been waiting for, and you may never hear it because we may just descend into absolute mania and never finish this recording. So
the good news is that if we do descend into mania, predictive processing has a really good prediction for what would be going on, and this is why I like it.
Exactly. If you're listening to this, it's made it out into the world, then it means that at least one of us has survived. We've been to hell in a handbasket and clawed ourselves out with like MDMA or something. I don't know. The rest of the episode will explain all of that.
Yeah. Well, psychedelics will come into it at some point if all is well. There's just there's so many interesting tie-ins, right? And I think it's worth mentioning why we care so much. So my first impression is, as much as predictive processing or predictive coding or active inference or free energy formulations of the brain, and let me just say, those are all not entirely equivalent, but they're close enough for the purposes of this conversation. This account of how the brain works is so unifying and so compelling that I had a huge feeling of being completely isolated when I didn't see anyone else talking about it so much. And I think there's reasons for this, which we can get into, but one of which is just the terminology is oftentimes confusing. You use many similar words which refer to completely distinct concepts, right?
Okay.
And so a big part of the reason for doing this episode is because I want to, do a tiny part in bringing this theory out and talking about it just in wider circles, because I think it's something that deserves more research and more thought. I think it can be generally helpful as a model of the brain to anyone who has one, which I presume most of our audience does. Most, if not all, let me add.
If that's not the most backhanded compliment I've ever heard. I don't know. Wow, incredible.
Yeah.
If you are like an energy guru listening to this from some other dimension, then we're sorry for any offense we've caused you.
Entirely. Please don't cancel me on
brainless slime mold. All right.
Okay, so I guess the place to start is just with a rough outline of where we're going. So we'll try and give the TLDR on what predictive processing is. We'll try and define some of these terms, and then it will become not entirely a free-for-all, but we'll go through some of the predictions that this model of the brain makes in terms of like the phenomenology, what you actually experience, and the evidence we see for this. I think there are amazing tie-ins with pathology of the brain. And if we can get to it, we can then see how maybe we could look at fixing that. And along the way, I think the theory provides a sort of compelling account for action and for perception and unifies the two in a really interesting way.
Awesome.
Cool. So let's just start with the classic view, you could say, of what our brain does. And the spoiler alert is that this is probably wrong. And at least if you take predictive processing seriously, it's entirely wrong, right? And so the way that growing up and through your life, most people tend to view their brains, right, is there's this outside world, and our senses do a good job of just taking a stream of incoming data and representing it to us, right? And we are viewed as this sort of internal viewer of this objective outside world, right? And so, like, just to take the eye, for example, the photons that represent something about the world hit it, and some processing goes on at each level, and at each level we pass more and more complicated features of the world up, at which point, when they hit somewhere in our visual cortex, they become a full, relevant, and detailed representation of that outside world, right? So it's entirely based on the brain as some detached object that receives sensory inputs, right? You think that's about a fair characterization of it? Of
the sort of conventional view.
Yeah.
Yeah, I'd say it's the idea of like the brain as a classical computer with some sensors that read in data from outside. I'd say that's reasonable.
Right. And so what we're doing with predictive processing is essentially flipping that on its head. So
that counts. That was a pun. You do secretly like them.
No, I don't. Anyway, basically what we're saying is that it's not enough to view us as these external independent observers who are constantly sampling the world. You actually have to give us a place in the world. And we start by generating a model of the world, right? And so our top-down model of the world, right? The model of the world that we start off with somewhere in our cortex, let's say, we push down through the layers, if you can bear with me for the loose language for now, such that our model meets the incoming bottom-up sensory data. Let me try and say that more succinctly, right? You can, in the classical model, we just had sensory data coming into the brain, and it was processed at each level, and that processing added detail and nuance and made that model useful in some way, right?
Yeah.
In predictive processing, what we're saying is we've got these two streams, and they work in opposite directions. You have the traditional bottom-up, right? Sensory data coming in, being processed at each level, and having the features added and integrated, right? But crucially, we have this top-down part, and the top-down part takes the form of a generative model. This is a model that encodes priors or prior beliefs or prior knowledge about the world and uses it to predict this incoming sensory data.
I think it's important to just clarify exactly what we mean there by top-down versus bottom-up. I think people have an intuitive understanding, but there is a little bit of like formal denotation here that is actually useful in this discussion.
Go for it.
Yeah, so just to clarify what we are talking about when we use the terms top-down and bottom-up here, there are two different modes of any kind of cognitive processing, but you could take it in the form of attention, for instance. With the case of top-down, it's voluntary, goal-driven, and it causes strain. It's something like doing mental arithmetic, whereas bottom-up is this sort of effortless, stimulus-driven, reflexive processing. That's like when you turn around to look at something that made a noise, for instance. It's kind of just a reflective behavior. Would you say those are fair characterizations?
I actually don't think they are. And I think it's not because you're wrong. It's because, and again, this is why this area is so fraught in terms of explaining it. It's because two different branches of neuroscience or cognitive psychology have both decided to use the same words to refer to different things. It's not because...
Right.
So this is just one of those cases where we have to play Rationalist Taboo and determine what we mean by the words. So
okay, so the unintended side effect of trying to clarify terminology is that we realize that we actually were using the same terminology to mean different things. So this is useful. Okay.
So some of the things you said are key, but the main thing is, for example, top-down doesn't have to be voluntary in predictive processing. In fact, most of the top-down part of predictive processing is involuntary, right? You don't choose that your brain develops this world model. Whereas from what you say, it's, as you say, it's top down, it's this voluntary feeling of movement or action as opposed to reflex driven bottom up.
Right.
That's not what I'm referring to. When I say top down and bottom up, it's very anatomical. So it's literally in the sense that from the bottom being the most external distal sense organs, right? Your eyes, your skin, the receptors in your joints, right? The taste buds, right? So it's the most external from your body going in, right? So you can just trace the nerve, right? And that nerve will go from, let's say, the bottom, like your eye, through your brain and up to the highest layer, which we're calling the top here, which is the cortex. And so it's not purely anatomical because, first of all, the brain is a weird shape. And so you can get inside parts that are more involved in the top-down part. And I mean, it's not purely anatomical, but it's functionally anatomical, right? The cortex is the highest layer of the brain, and that's why it's the top. Let me say it like that.
Okay, so by analogy, it would be top down is going from deeper layers of your neural network to shallower ones, and bottom up is going from shallower ones to deeper ones. So top down is sort of conceptual down to sensory, whereas bottom up is sensory up to conceptual.
Exactly. Perfect way of putting it.
Got you. Okay.
So, and if we have to do that several times in this conversation, we apologize, but it really is worth getting the terminology correct here, because much of what took me so long to learn anything about predictive processing or predictive coding is that you run so quickly into thinking you know what a word means, and then it's actually because there's this extensive literature where everyone's agreed to use one specific meaning, and no one tells you that until you've read a lot of it, and you kind of
even the name itself, I mean, it has two names.
Yeah.
And I'd wager, I don't know this for a fact, but I'd put prediction on this, that predictive coding was the original name and is the sort of de facto one, but predictive processing came about because it alliterates, and the brain definitely has enhanced memory for certain kinds of things, such as alliteration.
Yeah,
right, like
that
a term like
case.
yeah, like predictive processing just has much more punch to it.
So what have we got so far? Well, we've got this top-down model, and at this point, maybe it's worth making the sort of tie into Bayes' theorem and how we think about that, because on some level, this theory is deeply tied to what are called Bayesian approaches to cognition or to the brain, right? And sometimes more generally just Bayesian brain hypotheses. And so like, what do we mean by that? Well, if you think about Bayes' theorem, and if you've never heard of it, don't worry, we'll do our best to just walk you through the key pieces you need to know for this. But Bayes' theorem, the TLDR, is it encodes the optimal way for us to update our current model of something based on new information, right?
Yeah.
And the way that's sometimes put in the way that the formula is written is you take your prior, which we're calling the model here, and you have conditional updates, right? And once you apply an update to your prior, you get a posterior, right? Which is just to say your new improved model given some new sensory, or not, let's not say sensory, but just given some new evidence.
Exactly. So like a concrete example here would be, let's say I ask you to predict how likely, or what's your level of belief, because that's the key idea with Bayesian reasoning, as you're talking about your degree of belief, as opposed to infrequentist statistics where you're looking at like, samples and population averages. If I ask you to give your degree of belief that Donald Trump wins re-election, and let's say you go, okay, just intuitively, you feel like there's probably some bias in favor of the incumbents. So you're like, okay, cool, I'll call it just as a base, as a rough start, call it like 60% chance, right? Your political preferences aside, it's a prediction of what the outcome will be. But then you see that you get some new information, which is that the impeachment was, expunged, thrown out. Essentially, the Senate overruled the impeachment and said, okay, he's impeached, but we're not prosecuting him in any way, right? So he continues to be president. And you've read somewhere that if that happens, it increases his chances of winning re-election. So now you've got this new information, and what you do is you take your pre-existing sort of hypothesis that it was or belief that you had of 60%, and you now update it with the new information. And Bayes' rule is just a way of expressing how to do that in a formula in a statistically sound way. So you would then go, okay, that increases his odds, and you run it through the formula and you find it comes to like 65%. But aside from the formulas of this and the sort of rigorous way of doing it, there is also a kind of intuition about it that you can apply in your everyday life. And it's definitely a beneficial thing. It's something we've spoken about at length in previous episodes.
Yeah.
But the core terms there are, whenever we talk about Bayesian, we're just talking about a kind of probability that represents your degree of belief in something. When we talk about priors, we are talking about your sort of first approximation when you don't have particularly good information yet. And then posteriors are your updated belief that takes your initial prior belief and incorporates some new evidence you've got to have an updated posterior belief.
Right.
Is that a fair summary there?
Yeah, perfect. And now the simple move that we're going to make here is it's sort of a short leap to now map that onto the brain, especially with this top-down, bottom-up architecture we're talking about. So in this case, your prior is just your current world model, right? But we're saying that your top-down processes are encoding, right? Then the conditional updates, right? The new evidence is whatever your senses are telling you, right? And then wherever those two meet, right? Wherever passing new information from my senses up my nerves meets this propagating top-down model, right? Whatever my prior is encoding, they meet, somehow perform a Bayesian calculation, or maybe something that approximates it, right? And there's an interesting debate in neuroscience about, is it approximation? Do you have to just have some way of integrating the evidence? But just mathematically speaking, there's no way that you could update the evidence that is more optimal or just better than doing pure Bayes. So
yeah,
it's got to be doing something near it, right? Well, at least that's one way of thinking. And once you apply this new data to your top-down model and adjust your model, you've got a new improved model, which we can call your posterior. So you can see that maps quite naturally onto separating the brain out into top-down and bottom-up, right? And that's why already at this level, without too much in terms of predictive processing, right? I mean, at this point, we've just reduced the brain to doing something akin to Bayesian reasoning. And already, I think this makes more sense of the world than the pure bottom-up model that we introduced in the first few minutes.
Definitely. Yeah, of just having purely sensory input. Because without some conceptual representation, it seems difficult to have long-term goals be achievable.
So maybe it's worth now digressing for a bit to think about why we have brains at all. And as we think about that, that might give us some clues as to how, if you were to construct one, you might construct it so that it achieved those goals. And so obviously the key thing to note is that the fundamental drives of an organism are to survive and to reproduce, right? And so our brains, we should expect, should contribute to that. And there's lots of obvious ways that you can say that brains help us survive and reproduce. But if you had to distill it down into one thing, I think it would be fair to think of all of cognition, all of the fancy mental machinery that we have, all of it is in some sense cashes out in moving or contracting or relaxing muscles. Like fundamentally, what we do in our heads has to cash out in muscle movements. And before you object about what about imagination, we'll put that aside for now and notice at first glance, most animals and most other creatures, whatever their brains are doing, it cashes out at the level of twitching, contracting, and extending muscle fibers, right? And so what I'm getting at is that we're fundamentally driven by actions, and specifically actions that are beneficial to us as organisms.
Yeah. Well, I mean, if you have no way of interacting with the world, then you're essentially just a brain in a vat, right? You've got you can sense, you can think about it, but you can't interact with it at all, which means you can never pursue any goals. So for anything to be able to interact and influence the world in any way, it's got to be interfacing with it. And so the terminology here when you're talking about like general agents is you have sensors, which bring in your information from the world, sensors. You then have some kind of internal processing, and then you have actuators to then interact back with the world again. So in the mapped onto humans or onto animals, the actuators are our muscles, right? Like even if you like want to, tweet some idea out into the world, well, you have to physically type that tweet out or voice note it, or you've got to move a muscle to actually make that happen for now.
Well, exactly.
When we get to brain-computer interfaces, then we've just made the actuator non-musculature. Well, we've removed the muscle as an aspect of the actuator. Now the actuator is some hardware device. So the idea is still perfectly valid. But
right. What we're getting at is that our brains are not, as you say, these isolated systems in a vat. We are like fundamentally connected to the world in a way that means that we should expect that the sort of classical view, which is like weirdly dualist, right? Where you've got pure mind and then the physical world, right? The sort of Cartesian way of thinking of things. That's probably wrong, right? And the reasons for this include the fact that we should view ourselves as these embodied agents that are trying to affect the world, right? So that's just a brief digression onto what brains are for in some sense, right? And if we had to tie that back into this predictive processing part, or at least where we are so far, this part of having a top-down model, having a better model of the world will allow you to take more beneficial actions, right? Like if you think about it, the ability to understand something vital about the hidden underlying causes in the world means that you can take more meaningful and beneficial actions in the future.
Yeah, I mean, undoubtedly, right? If you have no way of, fundamentally, you want to be able to make predictions over time that are more accurate on average than inaccurate, because that means that you are essentially able to forecast the future on average. And the better you are able to forecast the future, the more accurately, the more your actions are going to align with what would have been the best action if you knew what the future was going to be, right? Like if you're looking back, and here comes another 2020 pun for you. No, I'm kidding. I'll spare you the punishment. So if you're looking, you never get away with it. If you're looking back, it's pretty clear in most cases what the best action would have been. If you're playing a game of like chess, for instance, and you look back and you just lost the match because you moved something in the wrong place, you can look back and go, okay, well, that was not the best action. It would have been way better if I just did anything else, because at least you would have survived one more move. And in most cases, a best optimal move is valid. You can look back and go, oh, that would have been the best move. So if you can predict the future with some high accuracy, you're essentially able to look back at the present from the future. Like that's the ideal sense. That's like perfect clairvoyance. Like if you know exactly what the future holds, you could tell exactly what the best move is. And the closer you can predict that, on average, the closer you get to making the best moves, which leads to your goals being achieved, right? So for any agent, any system, that's the goal, and getting closer and closer to that is kind of the objective.
So now that we've got those things sort of under our hats, I think we should just go outright and sort of say what predictive processing says. Now that we've got this idea of top-down and bottom-up, and of a generative world model that in some way encodes our best current understanding of the world or our prior beliefs about it, right? What does this all tied together look like? Well, what it looks like is it says that cognition or perception is fundamentally about trying to predict our incoming sensory experience using our world model. And so what that means is at every level, the layer above, right, the top layer, is trying to predict the inputs from the layer below. So the retinal ganglion cells are trying to, in some sense, predict the incoming light, right, that sensory stimulus. And the cells at the layer above that are trying to predict whatever stimulus they are about to receive from those ganglion cells, all the way up to the top layer of all, which is the visual cortex, let's say, which is trying to predict the inputs of the cells in the layer just beneath that.
Exactly. And this is exactly on a conceptual level what a neural network is doing at the broadest conceptual level. You're just having each layer interact with the layer in front of it or before it, and only that layer, right? Like there's no way to just jump immediately from your sensors to your model. Like it's got to trickle through these different layers of the network. That core idea is the similarity between artificial neural networks and biological ones.
Yeah, of course, the big difference here being that the artificial neural net doesn't have this predictive world model. And in fact, that was a big subject of discussion in the episode prior to this, right? 2 episodes prior.
Yeah.
So
let me clarify there.
Yeah.
The contents of the information that's being passed between layers can differ between the two, and does. But the core idea of
passing
you
information.
can't just exactly. It's got to go through all these layers, and you just essentially have to just look at the layer in front of you or behind you, depending on what you're trying to do. And if you can in this case predict the next layer, then and the layer in front of you can predict the next layer, and so on and so on and so on, you achieve the same overall result as if you could predict the final outcome, because it just trickles down from each layer.
Yeah. And of course, it's worth just saying, or caveating this and saying, of course, there are more complexities in the actual brain that we're kind of glossing over here to present a nice, simple model, right? I mean, there's long-range connections in the brain. There are recurrent connections. There are, first of all, like it's not necessarily this neat hierarchy, but
yeah, which is also true in lots of artificial neural networks these days as well. But we're talking about core concepts here, and then we can elaborate later.
So now, if these layers are trying to predict the inputs of the layers beneath them, well, why does that work and what's important about that? Let's see if I can get at that. So the first thing is that in this model, if you successfully predict the inputs that you'll receive from the layer below you, then in this model, you're allowed to ignore that, right? And that makes intuitive sense, right? If you learn nothing from what that layer gets you because you've predicted it already, you don't need to do anything, right?
Yeah, it doesn't give you any new information.
Exactly, it's as you expected. And so what is passed forward in predictive processing is not actually, and here's a really key point to flag, right? If you remember, we said that in purely bottom-up views of the world, the sort of naive view we were talking about at the start, you actually pass literal features of the world up through each layer, right? In predictive processing, we never pass features of the world up. We only pass parts of the world we didn't predict already. We pass prediction error. It's another way of saying that. And this is so key to the whole model, right? We're never passing features of the world which are then processed and then integrated into larger features which are then integrated like a convolutional neural network. What we do is we pass whatever parts of the incoming sensory data that we didn't already predict. And then this is where it becomes sort of multi-level, is let's say you've got a layer and it predicts most of what the layer beneath it sends to it, right? Now, there's obviously a prediction error, and it passes that prediction error, right, the unpredictive part of the incoming sensory signal, forward to the layer above it. Now, the layer above it is trying to predict the inputs that it gets from that layer. And so it's trying to predict, if you think about it, it's trying to predict the error as well. And so if the layer above actually predicts that the layer below will make an error, then that error still doesn't get propagated forward. It made it one layer up, but it didn't make it all the way up. And so every layer is trying to predict the unpredicted parts of the signal that it's receiving. And so the only thing that eventually gets passed all the way up is fully unpredicted information, right? And this is what will be integrated into the highest level of your model.
That's super cool. So that's the key nugget of what makes this really special. Is it's only the things that were unexpected are being propagated through and being used to update. Okay. And just to clarify on terminology here, by prediction error, you literally just mean the difference between what you predicted and what the actual value or outcome that was observed was.
Yes.
So you could literally just take observation minus prediction, maybe take the absolute value of that kind of thing. In the simplest sense, you might wrap that in a certain way depending on your implementation details, but essentially it's just the magnitude of the difference between your prediction and reality.
Yeah, I mean, there's probably some complicating factors in terms of how you represent this error, but for the simple value of thinking about it, we can say that's roughly what we're doing here. And of course, some people here are thinking about this and going, okay, great, but how is the brain doing this? And let's just flag that, and we'll say we'll do our best to come back to it. But the spoiler alert with anything in theoretical neuroscience is that if we really knew, well, we'd be done by now as a field. So clearly there are some big problems that we are yet to get to. But again, this is worth just explaining because of how valuable this seemingly banal insight actually turns out to be, I think. Okay, so currently we're at the point where we've gone from a naive view where we pass the world through our neural network, right, our brain, to now we only pass the parts of the world that our internal model doesn't predict. We pass prediction error. Okay, so how does that cash out? Well, first of all, it means that what you think you're perceiving, right? So think about what it means to perceive something under the naive model, right, where you're passing the world through, right? And at the highest levels, you've just got this well-integrated, high-level picture of the world, right? Then perception in that model is your view of that world, and it's entirely generated by these bottom-up signals. Perception in our predictive model, because it's entirely based on a generative prediction, means that what we're seeing is what we predict and anything that we then don't predict and have to integrate into our top-level model. So the reason that's interesting is because if I'm explaining it right, you should get the sense of having your view of the world inverted. Instead of feeling like you're this observer looking out at a world, you should feel like you are you are generating a world and then sampling some external thing which confirms or refutes that generated model. So that's interesting on so many levels because we can tie that in phenomenologically, right? So here's a really easy way to do that. If the purely bottom-up notion of experience was true, right, then at every level we would only be able to access, right, things that were in the outside world. You know, if me looking out at my desk right now was entirely driven by that bottom-up process, then the only elements in that scene should be physical ones that are out there in the world. But this is an experience familiar to almost everyone. It's possible, right, to say, okay, well, imagine looking out at the desk and now just project mentally the image of a small monkey sitting on the edge of it or something. So some people have really vivid imaginations, but most people will at least acknowledge the sense that there's something there. And we can recognize it as mental, but the point is that we're overlaying parts of something that is definitely only in our mind in what we have previously supposed to be something in the external world. And what's important to notice about that is that should phenomenologically refute the notion that what we're looking at is an external world, right? The fact that content that we know is purely mental, right? This imagined monkey, the fact that it can be overlaid on what we thought was the external world, right? The image of a desk in my mind has to mean that this desk I think I'm seeing external to me, right, is in some sense internal, right? They're in the same space, right? They're in a mental space where one can be overlaid on the other. And let me just quickly, before people call a psychiatrist for me, I'm not saying that the external world doesn't exist. I mean, there's something there, right? I mean, that's where we're getting these prediction signals from, right? Is we are sampling the external world. But what I'm saying is the thing that you're looking at is definitely inside your head, right? Because that's the only way for you to have projected this imaginary monkey onto that same space. This is difficult to explain, but it was one of the most fundamental insights into the workings of my own brain that I can ever remember having.
Yeah, and it's honestly just opens the door to so many possibilities and so many questions and so many new ways of approaching the problem. It's really cool. So let's just walk through this a little more, and just want to see that I've effectively ingested the ideas and that my model is. I'm going to sample from your observations here and compare them with my model. So essentially, what I got from that is we have this internal model of our environment, of the world, of any particular concept, right, that we're engaging with at any given time, and we then go and sample through our observations, through our senses, from the external world, whatever that might look like.
Right.
And we make these small point-to-point comparisons between that and our model. And when things are the same or very, very close, we're like, okay, cool, all's good. Ignore that. We're on track here. Our predictions are accurate. Our internal model is a good representation. And when we start making observations and comparisons that have big errors, big differences, then we start getting surprised, and this changes something in us that then makes us go and take further observations and update our model, right? So would an example of this be when you go and you're making coffee and you reach to pick up like the carton of milk, and you think it's full, but actually in the middle of the night someone's like drunk most of it, so it's like almost empty, and you like reach to pick it up, and because you think it's full in your model of the world, and then you reach to grab it and lift it, you end up like picking it up really rough and hard and being really surprised at how light it is. Would that be an example of your model of the world and the observation were like mismatched, and then you get surprised, and then that causes you to update your model and go, oh, hey, I guess someone drank the milk. The milk is actually empty when I thought it was full.
Yeah, perfect example there.
Okay.
I guess it's worth, again, flagging. So we've already spoken a few times now of how this field is fraught with words having more meanings, in the technical context and then in the sort of more casual context. So surprise and prediction error sometimes do literally cash out into the feeling of surprise, right, that you would have when the milk carton is empty. But a lot of this is subconscious, subpersonal, and surprise in the technical sense is just, one neural layer receiving unpredicted sensory or unpredicted information from the layer beneath it. And so just see if you can, as we go through this conversation, keep in mind that sometimes the feeling of some of these words is not always associated with the technical word, in which we just mean a more mathematical notion of surprise, right? Like something unpredicted.
I think there are a lot of terms in these sort of areas that are very misleading, and it's very easy to use the colloquial sense and then unintentionally be referring to some technical sense. So two examples of this are attention and surprise. So those two words have varying technical meanings depending on which experts you're talking to and whether they're looking at brains or artificial neural networks. But they also have two very well-known colloquial meanings, and so it gets a bit tricky. So I definitely shouldn't have used the word surprise to refer to what I felt picking up the milk carton in this context, because that does confuse things and make this all slightly more opaque. So, okay, noted. Surprise is a loaded word here, as is attention, and we'll probably come to both of those in a bit. But as a general idea, this already seems really interesting to me, this idea of you create some model of the world, and if your model is accurate, then you don't have to change much. It means that you're consistently, you've encoded your environment in some simpler, more compressed notation, right? And part of this rings of the value of like humans' intuitive physics. Like we all have this intuitive sense of physics that we've developed through just playing and interacting with the world. It's what allows us to catch balls. It's what allows us to, walk and things like that. It's what allows us to know how to use leverage in the physical world quite well, just without even thinking about it. and a host of other things, right? We're able to function and make these predictions about how objects will behave when they collide, when they fall, various things like that. And so we've essentially encoded some of the, at least Newtonian laws of physics into our subconscious perception or model rather of the world. And that seems like a really useful thing to do, right? Because that means that your internal model is going to be pretty accurate because those laws are pretty consistent in terms of how the world usually complies with those until you like go into gigantic scales, right? So for most of your daily life, your intuitive sense of physics is actually a pretty good generative model of the world for many ways you interact with it. And so then you just sample from that. But occasionally like things go off with your observations because you didn't account for something being a lot heavier than it actually is, or, things like that. And so intuitive physics seems like a good example here. And why this is really interesting is because it means that you don't have to do as many observations to be able to model the world effectively. If you had to completely rebuild the world every moment of your awareness, right? So let's say every like 100 milliseconds, just as an example, right? If you had to rebuild the world entirely based on observations at 10 hertz, you would never be able to do anything. Like, have you ever seen those renderings of like really primitive LiDAR, which is like the laser distancing system that some self-driving cars were using? Like they're trying to like detect objects nearby and it builds this really crude 3D map just from all like the nearby points. And you can't tell what's going on. You can vaguely see that there's some general straight thing that might be a road, but you can't really see much at all. Whereas if you have this existing inbuilt model and then you're just making like comparisons to check that it's still valid, it means you don't have to constantly be rebuilding that, which just seems like a much more efficient way to be encoding a model of the world. And it seems like it is, not only just more efficient, but just allows you to act more speculatively, which allows you to test like long-term goal assumptions and things of that nature, which is really, really interesting.
Yeah, 100%. So what I think is useful is just while we're on the topic of these phenomenological pieces of evidence for the general theory, let's just go over some other ones, right? And the most common, or rather the most compelling, are visual illusions. So take the hollow mask illusion. A lot of people will have seen it, but some wouldn't. But if you Google hollow mask illusion, you'll see images of what at least at first appeared to just be faces. And you say, okay, great. And what it turns out, if you had that rotated, you would see that the whole face has been inverted. But a funny thing about our visual systems is we never seem to perceive hollow masks as inward facing. We always somehow do something neurologically such that it pops out like a normal face would, three-dimensionally, with the nose the closest point to my face.
So we always see it as though it's facing us, not as though we're about to put it on.
Exactly.
Okay.
If you think about that, right, this is just another little thing that's refuting this purely bottom-up view of the world, right? Because if it was purely bottom-up, we would see that and we would see it as a reversed mask. But if you think about what that means, if you think about what's happening from a sort of Bayesian perspective, our prior on a face being right way out is so much higher than the prior on an inverted face that essentially that top-down prior overrules the incoming sensory data. And so what you instead get is basically you fudge the sensory data and make it say, well, I'm getting some sensory data that says that the mask is inside out, but my prediction error is minimized if, well, actually this gets a bit screwy because you ask why wouldn't the hypothesis that says the mask is actually inside out win, right? Because this is clearly a case where the prior on the mask being right way facing is so high that it's overruling your sensory data.
Yeah.
And so the question becomes like, how come then once you tell me that no, the mask is actually inverted, how come people can still look at it and it still looks like the mask is facing the right way?
Yeah, so there are two things there that are super interesting that I think are worth unpacking. The first sort of being why you would not want your sensory inputs to just overwhelm your hypotheses or your model at any point in time, right? Like why that just doesn't trump it immediately. Like why do we do this Bayesian update thing? And then the second is sort of this difference between like how you can know in some optical illusion what is true. Like you might know that the one line is, or that both lines are the same size, or you might know that the mask is inverted. But you don't like perceive it that way, right? And that's a different question that I think is interesting. But for the first question, this idea of why you would still want to use this Bayesian approach, right? If your internal model, your prior, is saying it's 99% sure, just arbitrarily, that the mask is facing outwards, that it's convex as you face it. Like, that makes a lot of sense. Like, faces almost always look like that. You pretty much never, in fact, you're never going to see a face from the other side, like a real human face, unless you were a pretty macabre type person, or you doing very niche kinds of dissections on cadavers, right? So like, yeah, so like it's pretty unlikely, and most of us have grown up not seeing inverted faces, and so there's very high likelihood. But then you have some sensory input that goes, hey, this is the other way around. Why would you not just immediately trust that? And I think the answer to that question is because of noise. Like, sensory data is not just measuring like reality, it's measuring reality with some noise getting in the way, right? Like, our senses are imperfect. The world has noise in it, that things that complicate the data. And so just as with a radar signal where you might not want to be detecting things that you think are incoming enemy missiles and then starting World War III. Like, for instance, you want to be quite sure, right? And so what you do is you have certain ways that you handle noise. And one of there are ways to do this. There's trade-offs that you can make with sensitivities and things of that nature. But another model of that is one that works through time, where as you gain more information over time, you can gradually refine your model. So this one data point that you get when you're looking at a picture of one of these hollow mask illusions, it's just one data point, right? You're having one observation. And so your prior that the face is facing outwards towards you simply will just like you are updating when you get the information from your senses that the face is inverted, but you're only updating a slight amount. So your posterior is like, say, 95%, but it's still the majority there. But if you then face one of these things in the real world and can physically like hold it in your hands and rotate it and look at it from different angles, well, then suddenly it becomes very clear which side you're facing the mask from, because you're getting so many new data points that every time, like every moment of awareness, you are updating that posterior probability, right? Your posterior then becomes the prior to the next estimation. So every time you're getting different kinds of input. And if you give it to a child, like that's what they'll do. They'll start rotating the thing until it makes sense to them.
Yeah.
Right? Or like you'll crane your neck or look at it from a different angle. So I think part of what makes this interesting as an example is that you see pictures of it and it's super confusing as an illusion. But if you were facing that in the real world, quite quickly your brain would switch to seeing it as inverted, because that's how it actually is. And your ability to like move around and look at it from different angles would allow you to update that model.
Yeah, although I don't know that even if you've seen the other side of it, right, so you can see that it's inverted, I think that's still, I've never had one to physically play with. So correct me if I'm wrong, if you have or if you know about it. But my sense is that even then, when you go back to looking at it from the correct angle at which to see the illusion, your brain still snaps to, oh no, that's a forward-facing face.
Yes, that might be true, right? But then essentially you're just returning to your. So this is the question of like how big are these models? How all-encompassing are they? And at what point do we transition between different models? At what point do you because if you go back the next day, your brain will still immediately see it at first as convex and then only as inverted after a while again, right? So clearly there's not just one model of the world. Like, there are multiple models here. And that second point that I found interesting was like, how do we then have this something else, this conscious awareness on top that can be like, oh, hey, like, I know this is an optical illusion. Like, I'm fooled by it visually, but yet at the same time, I can know because I've done the experiment of like measuring the two lines or touch or I know that this mask is inverted from other sources of information. And that can trump your perception in the sense that you still see it as the illusion, but you can know and you can then make other kinds of predictions about it in a conscious way. So it's like, are there different models here? Are there different hierarchies? And like, how do we switch between models? Like, does this all make sense under this Bayesian way of looking at things?
Yeah, so there's a really interesting way to think about switching between models here, because as you say, another word for model here could be current-based hypothesis, right? And of course, this is a probability distribution amongst hypotheses, right? So what you're doing at any given moment is selecting the top-down hypothesis that best explains your data. And then any unexplained piece of the data, well, that will first of all either help revise the hypothesis, or it will falsify it so outrightly that the only thing your brain can do is switch to the next best hypothesis. Thanks for listening to part 1 of our series on predictive processing. Part 2 picks up where we left off here and then dives into the glorious world of precision-weighted prediction error and perception action causal loops. I promise you it will be worth it. So tune in next week. You can find the podcast on Twitter at PodTangent, and if you liked it, consider sharing it. And so with that, we hope you're safe, and we will see you here next week for the next episode of Bit of a Tangent.